everybody. We're going to get started again so that we can keep on time and I'll go to lunch on time. We're really happy to have Tim O'Shea as our next speaker. Tim has two hats. He works at a company, works for DeepSig, and also he's a professor at Virginia Tech. He's been one of the pioneers of using ideas and algorithms from machine learning and deep networks in COM. In fact, Tim, all of us and our students have been reading your papers, so we're very eager to hear about what you have to say. So thanks very much. Take it away.
Thanks. All right. Well, luckily, Eric Stouffer just provided all the background on deep learning, so we can assume you're all deeply familiar at this point. All right. So I'm going to talk about kind of physical layer deep learning and applications in next-gen baseband processing for both sensing and communication systems. All right. So what are really the motivations? So we've been through many iterations of wireless here, and things have gotten fairly close to the Shannon bound. We have very, good performance in our current 4G and 5G systems. So what's the motivation for this? Where are the gaps, right? And so a lot of this comes down to complexity. So if you look at 5G systems, the number of band allocations, and you look at the number of antenna elements on next generation systems, you look at the density of devices in new areas, you look at the complexity of hardware impairments on top of channel models, on top of interference models, on top of distortion models, and you look at the drive to get costs and BOM costs down. These are all kind of a massive number of factors that we need to optimize systems for, and jointly, ideally. We'd really like the best joint solution for all of these constraints. And this is really something that's difficult to do in our traditional approach to comms, is to really take all of these things into account at the same time. So machine learning is really an interesting path forward. It's shown that the current kind of class of deep learning really can address optimization problems with millions or billions of parameters and of data sets of very, very, very high complexity and ill-defined kind of densities, right? And so this is an ideal tool for fitting these very, very complex, many, many degrees of freedom problems. And this is really the reason that machine learning is interesting here. Now, besides that, there are some really nice properties. So, when we build comm systems, we design typically analytic models that we optimize them for. Really, what we want is to optimize them also to operate in the real world the best that they can. And so, we'd really like to fit them to, real measurement data, real propagation data in the cases that the models don't match. And computational complexity is a big factor. So, inference and training can be expensive for some machine learning models. They can also be very low complexity. So some of the things we've seen are that when you train a lot of these machine learning models, you get very concurrent outputs. So you can wind up with very concurrent inference models, which wind up being potentially of running at lower clock speeds in a more distributed fashion, and often with less iteration, so just a forwards pass. So there's a lot of really, really nice properties here that hold the attraction to learn much lower power algorithms and solutions to many of the things that we need to do in signal processing. So these are really the motivators. So why would you want to do this? All right, so just a brief aside on DeepSig. So we're a 2-year-old company. We're focused really on leveraging deep learning at the physical layer to provide major performance improvements and to really show kind of the first major test cases of you can really do robust rapid wideband sensing, and you can really optimize over-the-air practical comm systems using these techniques and really building these out quickly. And so this is really our focus. We have a really awesome team that comes from the kind of Good Radio and the Volk and the NI USERP team in the past. Really the goal here is leveraging these data-centric machine learning approaches to build comm systems that scale and really can manage this complexity we just talked about. And so we're partnering with kind of key wireless system integrators to kind of provide components and to help trying to enable them to use and leverage these algorithms and software approaches. All right, so what are kind of some of the places where I think ML has huge potential to make an impact in the physical layer? And so there's really kind of two classes of this, and these are really kind of think about places in the baseband processors, in base stations, in modems, in sensing systems, where this can have an impact, right? And so there's kind of two classes here. There's understanding complexity, which is really having accurate models of channel effects. There's propagation models. There's security applications. So what's going on in the spectrum? Are there unauthorized emitters? Are there base stations turning on and off? Are there interferers operating in the band? And fault monitoring. So am I seeing PIM on my towers? Am I having hardware failures? These are all things that we're kind of blind to right now in most wireless systems, right? We kind of rely on higher order key performance metrics at the network layer, and there really aren't great ways to just recognize these things on the raw RF data, and largely because it's too expensive and costly right now to do that. But that cost is going down. So the other half is exploiting this complexity. So building comm systems which take advantage of all these degrees of freedom to do better in how they communicate over all of these different factors that are constraining the comm system and impairing the comm system. So this goes to improved modulation and coding schemes. This goes to improved resource scheduling and assignment within wireless systems. This includes kind of spatial encoding. How do you exploit massive MIMO and multi-user MIMO systems most effectively and with the lowest power algorithms? And really just how do you reduce power consumption? So if you can use more small, compact inference models to save power, this could have huge power savings in numerous baseband applications. And there's a million applications at the network and application layers, but those are kind of beyond the scope of our focus. But it's also a really exciting area looking at kind of MAC algorithms and routing algorithms and scheduling and caching and compression, as Eric was just talking about. All right, so I really like to look at computer vision as kind of a model for where we're going and what has happened in those fields and where we're headed in signal processing and comms. And so you've really seen this major transition happen from these compact domain models and compact expert feature models to very data-centric, scalable end-to-end feature learning models. And the first really major thing that did this was AlexNet, training a ConvNet on a very large raw image set. And since then, this has really kind of led the performance metrics in computer vision, and being able to exploit this amount of complexity in your data distribution it's really kind of been unmatched in other ways, since that transition occurred, right? And this was very contentious in computer vision, and it's still very contentious in comms and signal processing. But the problem is, if you want to exploit complexity, there's not a nice compact representation usually. And now there are ways to provide guarantees and things that we're used to, but if you want to exploit complexity, you need a model that can really learn all of the factors of that complex model. Right, so we've really seen this constant improvement and progress. So a lot of this is also, like Eric Stauffer was talking about, benchmarks and data sets are a huge piece of this. And you really just kind of, it's amazing when you have a well-defined task, benchmark, data set, you just see this constant progress of model improvement, training improvement, methodology improvement. And it's just kind of this performance that just kind of continues to scale. And so it's really exciting to look at this comparison at the bottom here of where we were in 2012 in computer vision, which is just kind of basic image classification in AlexNet, to today, where we have now these real-time image segmentation, object identification systems that are being used today in deployed computer vision systems for self-driving cars and other applications all over the place. And it's just really kind of incredible how quickly this technology progresses and just continues to get better and better and better and better when it takes on a field like this. And so, today maybe we're really just on the left side in comms, but think that we're really headed here over the next probably 4, 5, 6 years. So this is kind of the basic construct that is, it's one way to learn how to communicate over some channel, any kind of a communications channel. And so this, also Eric alluded to, this is kind of the autoencoder approach. And so here you're taking some symbols, S, and you're basically trying to classify the output symbol to be the same S. And you're going through this channel impairment layer, right? So this could be Gaussian noise, this could be Rayleigh fading, this could be a cost model, this could be any kind of channel model you really want in there. But you have this really nice property that if you can differentiate through this channel, you can now train a kind of nonlinear encoder and decoder network to learn any kind of encoding to try to really just minimize the bit error rate of this system. And so what you see here is basically training a simple 2 bits into one complex symbol system. And you see that as it minimizes the bit error rate, it kind of stabilizes on a really nice canonical QPSK constellation. And so this is just a kind of a nice proof that okay, it converges to something that we know. This is great and understandable, and we can interpret it. So you can start to do this for a lot of other types of channels. This is kind of an example here where we've applied this to a nonlinear channel with AM/AM and AM/PM distortion. And we show that if you learn an autoencoder model, it can outperform a number of kind of traditional modulation types just by fitting to the nonlinearities better. So there's a lot of nice properties of this. Basically, the really nice thing, you can kind of choose any information rate you want. So depending on how many bits you're packing into how many symbols, you can basically design a comm system of any information rate. And so here we show you can kind of converge to a number of canonical, QPSK, PSK, and non-standard looking QAM constellations, depending on your information rate you choose and the regularization that you choose for your modulation. So if you compare this to kind of baseline measures, you compare this to uncoded BPSK here, you see for a single symbol, you equal the performance exactly, but for a larger block size of 4 symbols here, you actually get this coding gain, which diverges from the baseline. And you've actually learned basically a small block code on top of that BPSK inherently that gives you this coding gain at a very, very cheap computational level. Same thing if you look at a bigger size, so if we compare this to a small kind of Hamming code on BPSK, and we look at the same rate autoencoder system, we can show that we outperform the uncoded, you outperform kind of the hard decision system, but you come right up exactly with the kind of maximum likelihood soft decoder. And so you can very quickly match kind of optimal solutions for various code rates. So the really nice thing about this construct is you can extend it to a number of different configurations. So we looked at, if you want to look at the non-orthogonal multiple access problem, which is really important as we look at scaling density in future wireless systems. There's a nice way to model that where you just have this mixture channel of multiple encoders, where the encodings become mixed with each other, and yet you're decoding separate sets of code words for each receiver. And you start to learn really crazy things. So the trivial case where you're putting a single bit into a single symbol, you learn this nice orthogonal BPSK representation. But as you scale to more bits into more symbols, you start to learn these really crazy kind of superposition codes of high order QAMs, which actually, if you start looking at capacity versus purely orthogonal codes, you get higher aggregate capacities. So this is exciting because if we deploy this in kind of non-orthogonal type wireless systems in the future, we could really improve wireless aggregate capacity using these sorts of approaches in combination with other degrees of freedom like spatial optimization and scheduling optimization. So one of the big complaints about this whole approach is we've thrown away everything we know about comms. We're not using what we know about PSK and about optimal organization of modulation structures and synchronization and a lot of the tools that we've used for many years. And so transformer networks are just a really nice way to impart things that we know and kind of expert domain knowledge about comms into machine learning in a way that we're assisting it and reducing the complexity of our model and our learning task, but we're not over-specifying it. So we're not losing the generality, because what we're doing is we're imparting kind of basic properties of radio propagation. So in this case, we know that these are kind of LTI systems. We have delay spreads that we can convolve the inverse to equalize a signal. This is kind of always how we apply an equalizer tap. And so if we do something like in this case, we apply a parametric transform which takes in a set of estimated taps and simply does the convolution and outputs it. And if we implement that in a differentiable way, we can now jointly learn kind of an H estimator and a discriminative network to do symbol decoding as a joint process. And by imparting this transform, we've greatly simplified the learning task and the manifold that we need to learn as we train the estimation and discriminative tasks. And so this really helps networks generalize. It lets us impart what we know about radios and domain knowledge in a nice way, where we haven't over-specified this to any kind of modulation or set of reference tones or kind of things that don't generalize. All right, so one of the things we've been looking at, this is kind of a cool demo, is working with NASA on the TDRS system. And so in this case, if you look at the TDRS, TWT amplifiers, they go kind of highly nonlinear as you get into the compression region. And so this is kind of a cool idea. So if you want to push more data through this channel, you really just want to push the power way up into compression, but you need a constellation that behaves nicely there. And so rather than looking at kind of traditional linearization methods and pre-distortion, why don't you just design a modulation which results in nice constellation properties at the receive after it's been through that transform. And so this is an example where we're showing training such a system, and you kind of converge to this really non-standard, non-linear looking transmit constellation. All right, so one of the big problems with using autoencoders in real systems is the channel model, right? So we assume that we have a differentiable channel model. However, we don't always have that, right? If we're sounding some system in the real world, we just have measurements. And so a lot of the work that we've done over the past year is really looking at how do you take measurements and sounding and very quickly build a stochastic model for the channel that's accurate and is a generative model, so that we can now train on it an infinite number of times, kind of sampling from that channel distribution. And so modeling this kind of P of y given x of the channel is an important factor. And one of the solutions here that seems to work very well is training this as a GAN. And so GANs are very, very good at learning arbitrary distributions. And in this case, we're trying to learn this conditional distribution of P of y given x. And if we set this up for kind of a stochastic approximation network along with a discriminative network, which tries to determine, is this a real sounding sample or is this from our stochastic model, you can very quickly learn a good stochastic model for the channel, and then you can use this to train autoencoders in real over-the-air systems very quickly. So this is an example of OmniPHI, which is our implementation of basically an over-the-air autoencoder system. And this was actually we first kind of showed this 2 weeks ago at DicePan. And this is kind of a cool proof point, because we're now transmitting an autoencoder of the same information rate over the air within the same channel. It's time interleaved with a QAM baseline system at the same information rate, so you can compare the performance of the two. And you can see that as you increase the block size, you in fact do get this coding gain relatively for free over small blocks. And so it's great to see that, yeah, these systems actually do work in practice. You can optimize these and deploy them in real time over the air fairly quickly. And interestingly, in the bottom right here, you see the autoencoder constellation. And it really just looks like noise, right? So you've learned this kind of very high order QAM, and essentially a decoder is kind of an error correction map over these multiple symbols of higher order QAM, right? And this works actually really, really well. And so, we're working now on, you can really, there's a lot of extensions to do MIMO with this, to do rapid adaptation and online learning with this, and really to use portions of this to augment kind of existing commercial standards to really improve performance. in a more constrained way, and you have to work within the confines of the specifications. So there's so many applications to this over kind of SATCOM, backhaul, dense urban wireless, cellular applications, and resilient comms when you have interferers and malicious actors. And so there's a lot of different applications for this that we're really looking at. Where does this make the most sense initially? From a sensing side, we did some work a few years ago on, can you take the image approach to RF data? So can you take raw RF data and IQ data and do feature learning on it with the same sort of convolutional networks that we use in vision and learn better features than we use today to do signal recognition? And it turned out that you really can. And so you significantly can outperform things like higher order moments and cyclostationary features, especially for very short time observations where you don't have a long time to integrate on those statistical moments to stable them. And so this has really been the path, right? So over the past year, is really scaling these machine models from toys up into full capabilities in the real world where we can vet these against wideband data sets, complex RF environments, and really start benefiting from this ability to leverage and exploit complexity. And so these are kind of a year ago and today for these two different capabilities. On the sensing side, RF sensing has never really been super practical for a lot of applications just because it's very specialized. It doesn't generalize well. It's usually kind of expensive and cumbersome to do robustly. But this is really, really exciting because if you take a machine learning approach, you finally have a very low latency, kind of low complexity ability to do wideband sensing and recognition of many, many different things. And so we've seen, talking to some people, that this solution is 100x speedups on traditional methods that they've used. And there's tons of applications for this in spectrum monitoring, and really building this baseline or foundation for rapidly consuming and structuring all of the information that's going on in the RF spectrum around you, and understanding it and doing analytics and responding and acting based on that information in our wireless systems. So deploying this, it's really exciting that computer vision is where it is. And because computer vision is creating this huge economy of scale for hardware and for architectures that we can leverage readily in the radio domain. And so if you look at basically the same class of ML models that are being used for vision inference and self-driving cars and your cell phones and many, many different platforms are really competing to be able to run these models cheaper and at lower power and faster and lower latency than each other one. And so we are really in a great place because you can take all these models, you can exploit kind of the best thing that's out there. And so, for instance, this NVIDIA Xavier board, is really built for computer vision and self-driving car sorts of applications. But it's really cool because we can take it, and we now have a very compact, very powerful inference model that runs for on the order of 10 watts, and you can really do kind of really fast real-time inference over the whole spectrum using this sort of a device. So if you look at cell phones as well, we're already starting to get the tools that we need down into cell phones. So if you look at a number of the cell phones recently have begun introducing kind of neuromorphic processors or tensor type accelerators. These are really the building blocks of doing inference down in compact mobile basebands, and this is kind of already in place. And so these are really tools that we can exploit and drop onto these platforms very efficiently. Right, and so these things are kind of software capabilities, but we've never. These sorts of data flow models have kind of a new degree of portability and efficiency across many platforms that we've not really seen before with other programming models efficiently. So it's kind of an exciting time for hardware deployment. So in summary. Machine learning is really kind of exciting simply because you can optimize over so many dimensions and with kind of richer channel models than you could in the past. You can really kind of build your systems to match their real world deployment behaviors so you can learn directly on the data when you deploy a system in situ, in cell, specifically there, rather than kind of presupposing and generalizing for all of your deployments. And there's really potential for significant power savings as you go to these kind of compact inference models, which are concurrent and can be low precision. But good data and good software are super critical to enabling this. And so these are really important things for the community to build. And so as part of that, actually, Jeff Andrews was kind of instrumental in helping us get this ETI off the ground, but there's this new IEEE Machine Learning for Communications ETI, which is really trying to look into helping coordinate and contribute to and provide resources in this whole area. Really kind of initial focuses of this whole thing are looking at helping provide more tutorials, publications is talking about a summer school, and really helping curate data sets and competitions and kind of baselines to help researchers really do comparisons and vet work in this field across different approaches, as well as kind of curate industry relationships and provide kind of a central place to help curate and provide a lot of research and reference information. Yeah, and so that's it. So come chat if you're interested.
Thanks a lot, Tim. Maybe one or two questions while the...
Hi, I have one question regarding the autoencoder approach. So we know that in standards, we standardize the waveform of the transmitter, and then the receiver is up to implementation, and that's where people compete with each other. How do you see, I mean, this will probably require a completely different approach to standardization. So what can be standardized in this autoencoder approach?
Yeah, so the autoencoder, how we've showed it is kind of like the full end-to-end problem. I think there's a lot of sub-problems you can optimize. You can either just optimize the transmitter, which kind of becomes a predistortion problem, or you can just optimize the receiver, which becomes a more kind of standard constrained problem. And both of those can still have major benefits. There's also a lot of cases where, like, if you start with standard modes and standard autoencoders, and then you allow links to adapt and update, within a local situation or cell or condition, where you can kind of maintain that interoperability, but then really benefit from improving online. So I think there's a lot of ways, and there's many ways to integrate this into the current kind of standards, and some are more extreme than others. So there's kind of a whole spectrum of how do you go about leveraging this in a standard and interoperable way.
I have a follow-up question. Thanks, Tim, for your nice talk. If one were to think about how to take these autoencoder approaches and how one could extend them or how one could impact a modern communication system, right? Do you have any thoughts on what it means to do this training in real time in, for example, a cellular network, for example? What does it even mean to train an autoencoder? And a follow-up question would be, how well would it generalize? Because what I would train in my lab may not be representative of a true radio channel. So how well will it cope with the uncertainties of the realities?
Yeah, and those are both kind of early. This field is young, so I don't think there's a perfect answer for how do you integrate this into a system. I mean, we have reference tones in all of our systems today that can be used for these sorts of training and error feedback processes now. So I think we can exploit a lot of what's there already to build these capabilities. And to generalization, I mean, this is kind of, it's not unique to comms. All machine learning problems really have to deal with generalization. And it's an absolutely critical topic when you're building your models and your training routines and dealing with how you treat data. You absolutely have to worry about generalization. So comms is no different.